Hey everybody, Mr. Bells here. I'm going to present to you a little bit of a lesson right now. This is on section 4-4 on transformations. And what we're going to talk about today with transformations is really something called a composition of transformations. So that kind of means putting one or more transformations together. So you know our basic ones right now, right? Reflection, rotation, and translation. We've discussed a lot. Glide reflection was one that was a composition of them. But that was just of a reflection and a translation. So now we're going to look at how do we combine maybe a couple of reflections, or maybe a reflection and a rotation, or those different things. Okay, so student journals are going to be good. Go ahead and use that. We're going to start on page 108. Before we do that, I'm going to throw this one out here right now. You could do that. If you don't have this down in your notes, that would be really good. Kind of give you just a bunch of the basic transformations in terms of flips and rotations and how the coordinates end up looking with it. You guys know that the translation ones or the vector ones look different than these because there's pluses or minuses with them, because those are just shifted up or down, left or right. These ones all affect reflections and rotations. Okay, so again, pause the video, copy those down. If you don't have those, just like that, they would be beneficial to you. Okay, we're going to start right here. I think I said 108. I really meant 109. So all of these shapes that we're talking about right now are ones that are going to be still congruent afterwards. Okay, so we're not changing sizes, we're not stretching them or shrinking them or anything like that. So the first theorem right now that we have that we want to talk about, and I think I've brought this up before, but I'm going to cover it again, reflections in parallel lines. So what happens when you take a shape and you reflect it over parallel lines, one line and then another? So you can see the first one. If we start with AB and we reflect that over this line right here, it's going to end up as A prime, B prime. A reminder again that this and this are going to be congruent, those two little segments, because it's going to be a perpendicular bisector from one point to another. And their shapes are still going to be congruent, but that is a reflection. However, if I take now this prime image, A prime, B prime, and reflect it over a second line, when these two lines are parallel, K being parallel to M, I'm going to end up with B prime, A double prime. And now you can see that if I look at the first one and I look at the third one, that the net result from those is a translation. Okay? You can see that B is translated exactly that far across, and A is translated exactly that far across. And it happens to be that that vector that we use for that translation is 2D long, where D is the distance between the parallel lines. Okay? So if D happened to be 4 inches, then if reflected BA over the first line and then B prime, A prime over the second line, then the entire translation vector would be 8 inches long. So that's our first theorem that we're going to use with. And you could check that, put some parallel lines down, flip it over one, flip the image over the second one, not the original one, flip the image over the second one, and you'll see that the net result from one to the other is a translation. And if you measure that translation, it's going to be twice the distance between the parallel lines. Good deal? Okay, so what's the next one? Next one's down here. It says, okay, what happens if you have AB, just like this segment right here, and you reflect it over a line K, you can see that it's going to end up just like this. Again, perpendicular, right? Perpendicular bisectors. And then you're going to take A prime, B prime, and you're going to reflect it over another line, M. It's going to end up right over here. So the net result of these two reflections, these times you can see these are intersecting lines, right? Intersecting lines. The net result ends up being a rotation. And here's the deal. However big this angle is, oops, sorry, make that a little straighter. However big this angle is, maybe this is 40 degrees. And again, I'm just making that up. It says nothing in here about it, but I'm just making it up. Say it's 40 degrees. Then the rotation is going to be twice that. 2 times 40 degrees, or 80 degrees. Okay? So, and that's true every time when two lines intersect. That if I take the smaller angle between the intersecting lines, that would be the acute one, and I double it, that would be the net result of that shape. And that's a quick, easy reminder from this, right? If I had a flag like this and I reflected it over here, it would go like this. Oops, sorry, let's make that look a little bit better, like that. And then I reflected this image over here and go like this, right? You can see that the net result is a rotation of 180 degrees. And why does it rotate 180 degrees? Well, because the lines intersected at 90 degrees. And that rotation will always be double, whatever the measurement is between those lines. Okay? So those are two theorems. Reflections, if they're intersecting, results in rotation. If they're parallel, right there, results in a translation. So now we're going to look at some basic shapes. And we're going to say, hey, how can I get from one spot to another spot? Is that possible? So I'll zoom that in a little bit better. Good deal. So like this one, can I get this to go right here? And hopefully your thought process is, yeah, I think I can probably do that. So then what is that? Okay, well, maybe I can get that shape onto that shape simply by, do we see this? Reflecting it directly over that line. That's the y equals x line. And you can see that point V, which is 1, 2, 3, 4, 5, negative 3, 5, negative 3. You can see point F is negative 3, 5, negative 3, 5. And all we've done is we've flip-flopped the x's and the y's, that this x becomes that y and this y becomes that x. And that's a reflection over the y equals x line. Okay? How do I get this shape right here onto this shape right here? Well, I simply can translate it. I can slide it over 1, 2, 3, 4, 5 boxes and down 2. 5 and down 2 puts it directly on top of that one. And then this one right here, I'm hoping that you can see this, that this shape, let me do this in green. Let me do this in green, that this shape could rotate directly on top of that shape right there. And that would be a rotation of, because it's really just going, watch, see this, point to point, you can see that that's 90 degrees, but it's rotating 90 degrees clockwise, which means, remember, that it's really a rotation of 270 degrees if we're talking about a positive one. So it's a negative 90 because it went clockwise. Clockwise is negative. Or a 270 degree rotation, which means that it rotated all the way back here like this. Is okay? So those are some of the things that we'd be looking at. So sometimes they're going to be ones that have a couple things put together on it. So you can see this shape right here, that this could rotate right to here 180 degrees. So that's a 180 degree rotation to get me to this spot. And then you can see that if I translated it, so 180 degree rotation, and then a translation of x's stay the same, right? But y minus 5, just like that. Straight down. If you wanted the vector notation, the secondary vector notation would be a 0 change for the x and a negative 5 change for the y. And that's pretty much what some of these other ones are doing, and I don't want to go through all of them. I want you to be able to try some of them, and you can try some of them on homework too. But these are being able to put multiple transformations together. And I know it's not super easy for you, but I believe the more that maybe you guys did some of these things when you were younger, or maybe you still do, if you could do some jigsaw puzzles, and you can fit pieces in, and you kind of look and spin and go, hey, I can do this and this and this with it, it makes it a little bit easier. This one right here, watch, I would ask this, I'm not saying this is right, I would just ask this, can this be a rotation? Can this be a rotation? And the answer is going to be no, it is not just rotation. Because if I rotated the shape up like this, you'll see that this little 1 box, 2 box, right? 1 box, 2 box side would have to be 1 box, 2 box over here, and it's not. It's like right there. So this isn't just a rotation. But my question for you is, what is it? Think about some different possibilities for that. Again, some of these you're going to get, some of them maybe you just can't visualize. But hopefully you can practice some of them and get some of them right on the homework so that you at least have a decent idea with these. Okay. And then here, I'm going to do one of these. I don't want to do both. But we're going to take the first one, A, 2, 2, B, 3, 1, and C, 1, 1. And then D, 2, negative 2. 2, negative 2. And E, 3, negative 1. 3, negative 1. And F, 1, negative 1. Are these two things congruent? It says congruent. And then it says be able to explain using a transformation. Well, I'm going to say yes, they are congruent, and because it's a reflection in the x-axis, that I could take it and poof, flip it right over. Now that would be that this triangle is congruent to this triangle. Now, with that being said, because these are isosceles triangles, I also could have had this triangle rotate 180 degrees right around the point 2, 0, and it would also end up. So then it's kind of, how do I list triangle, if it's triangle A, B, C, congruent to triangle, in this case, D, E, F. If I put them like that, so A is 2, 2, A is right there, B is 3, 1, B is right there, C is right here, and D is 2, negative 2, D is 2, negative 2, E is 3, negative 1, and F is right here. Okay? So, if I was to write this out that they were congruent, then A would have to match up to D, and that does. And B would have to match up to E, and that does. And C would have to match up to F, and that does. So the only way that I can list them like this being congruent is with that reflection. Okay? Now, if I was going to say that it was a rotation, then it would have to be like this. Triangle A, B, C is congruent to triangle. Okay, A would go to D, would rotate to D, right? So A would go to D. And then B would rotate all the way here to F, so B would go to F. And C would rotate all the way over here to E, and it would be like that. Okay, do you see the subtle difference between it? This says triangle ABC is congruent to DFE. This says triangle ABC is congruent to DEF. This one would have been a rotation to those spots to line up each one of those points. This one would have been a reflection. Okay, that's what we're going to get to later on with some stuff. Just kind of throwing it out there. So, again, just looking at some of these things, you guys know then, right? These look like they're parallel lines, and it says that they're parallel, right? And if I flip one to the other one and this one over the other one, then this resulting translation, right? This resulting translation should be whatever this distance is, whatever that distance is, that distance should be double it. Okay? good deal. Just like down here, on this bottom one, if we're getting from A to A double prime, that has to be a rotation because it was reflected twice over intersecting lines. And if this is 60 degrees, then this end result rotation should be 120 degrees, or twice the angle in between the parallel lines. Hopefully this has been beneficial to you. Please try the homework, stay on top of this stuff, make sure you're taking good notes. And Mr. Bells, I'll talk to you later. Bye.